In this video, we are going to evaluate integrals using trig substitution, and particularly with sine. But before we begin, let us understand the associated triangle with sine. Be sure to stick around until the very end because I will show you a quick shortcut for evaluating integrals using trig substitution. So we know that sine of an angle takes on the value of the side opposite over the hypotenuse. So opposite of the angle theta is x, and the hypotenuse is a. And now I want to use Pythagorean theorem to solve for the missing side. How about I let the missing side be called b? So I know that b squared plus x squared is equal to a squared. And this is by Pythagorean theorem. So solving for b, we have that b squared is equal to a squared minus x squared. So b is equal to the square root of a squared minus x squared. So this side is going to equal to a squared minus x squared. The side that we have solved for is your indicator for how to choose the sine equation and its associated triangle. Next, I want to go through the steps on how we make our substitution and rewrite the integrand. So the first thing you're going to do is you're going to find x and dx. So we're going to find x and dx. We see that we have sine of theta is equal to x over a. So I'm using that. Sine of theta is equal to x over a. Solving for x, we get that x is equal to a sine of theta. Next, we find dx. So if I take the derivative, that will be dx is equal to a cosine of theta d theta. Next, I want to find theta and its associated range. So we're going to find theta and its range. So again, beginning with sine of theta is equal to x over a, we have that sine of theta is equal to x over a. And if I take sine inverse of both sides, we get sine inverse of sine of theta is equal to sine inverse of x over a. So the left side of the equation will become theta, and that will equal to sine inverse of x over a. Now we want to identify the range of theta. Well, in order to find the range, we need to know the range of sine inverse. If you remember the graph of sine inverse, we know that the domain is from -1 to 1, and the range is from -π/2 to π/2. So this is how the graph of inverse sine looks like, something like this. So we see the domain is from -1 to 1, and the range is from -π/2 to π/2. So we say that theta belongs to the interval between -π/2 and π/2. What this essentially means is that if you were to look at the unit circle, here is -π/2 and here is π/2. So my values can only be from this right region of the unit circle. Now what I would like to show you is how to rewrite the integrand. Then I will get into an example. So we will look at the side of the triangle that we solved for and start here. So we have a squared minus x squared, and that's equal to, here's the value for x. X is equal to a sine theta. So I'm going to replace x with a sine theta. So this will be a sine theta squared. So this is equal to the square root of a squared minus a squared sine squared theta. And this is equal to the square root of, if I factor out an a squared, we get a squared times 1 minus sine squared theta. Now I'm going to pull out a squared, so that's going to become a on the outside times the square root of 1 minus sine squared theta. And by the Pythagorean identity, we know that 1 minus sine squared theta is cosine squared theta. So this is equal to a times the square root of cosine squared theta. And the square root of cosine squared theta is the absolute value of cosine theta. So this is equal to a times the absolute value of cosine theta. But remember that the value of theta belongs to the interval between negative pi over 2 to pi over 2, which means that theta must exist from the right region. That means that cosine must be positive anywhere between negative pi over 2 to pi over 2, because cosine takes the x values. Remember, cosine takes the x values of the unit circle and sine takes the y values of the unit circle. So the x values are always going to be positive. So this will equal to a cosine theta, since theta belongs to negative pi over 2 to pi over 2. Then cosine of theta is greater than 0, which implies that the absolute value of cosine of theta is equal to cosine of theta. So in conclusion, the square root of a squared minus x squared is equal to a cosine of theta. Now that you have the background of trig substitution, we are ready for our example. Now we are ready to work our example. I have kept everything on the board that is necessary and important. So for our example, we have the integral of the square root of 25 minus x squared dx. So the first thing you want to do is you always want to be able to identify which triangle and trig equation that you're going to use. Clearly, I see that this integral is set up in the form square root of 5 squared minus x squared dx. So clearly we see that we are going to use the sine equation because 5 would represent our a in this case. We see it's in the form a squared minus x squared. Once you identify the triangle, go ahead and draw it and write the trig equation next to it. So my triangle is going to look like this. And I know that we are working with the sine equation. So we have x here, and a is going to be 5. And on this end, we're going to have 5 squared minus x squared. And my trig equation is sine of theta is equal to x over 5. So we will be using this to help us evaluate the integral. Now I'm going to go through the steps that I showed you previously in order to make our substitutions. So first I'm going to find x and dx. So starting with the sine equation, we have sine of theta is equal to x over 5. And when I solve for x, we get that x is equal to 5 sine of theta. Then when I take dx, we get that dx is equal to 5 cosine of theta d theta. Now I want to find theta and its range. So if I were to find theta and its range, I'm going to again use my equation here. So we have sine of theta is equal to x over 5. And when I take the inverse of both sides, we get that theta is equal to sine inverse of x over 5. And theta belongs to the interval between negative pi over 2 and pi over 2. So knowing the restrictions of theta will help us rewrite the integrand. So now I'm going to come over here and substitute x for 5 sine theta, and I will substitute dx for 5 cosine theta d theta. So coming over here, we have the integral of the square root of 25 minus x squared dx is equal to the integral of the square root of 25 minus the value of x, which is 5 sine theta, and we square it, and dx is equal to 5 cosine theta d theta. So this is multiplied by 5 cosine of theta d theta. And now just squaring the 5 and the sine, we have 25 minus 25 sine squared of theta times 5 cosine of theta d theta. And this is equal to the integral of the square root of, factoring out 25, we have 25 times 1 minus sine squared theta times 5 cosine of theta d theta. And now I can remove 25 from under the square root. So this will become 5 times the integral of the square root of 1 minus sine squared theta times 5 cosine of theta d theta. And multiplying 5 and 5, we get that this is equal to 25 times the integral of the square root of, and 1 minus sine squared theta is cosine squared theta. And we multiply that by cosine of theta d theta. So this is equal to 25 times the integral of the absolute value of cosine theta times cosine theta d theta. We know it's an absolute value because we cannot have a negative number under the square root. So we must include the absolute value. But since we have restrictions on theta, theta is between negative pi over 2 and pi over 2. So that means that cosine will always be positive. Thus, we can remove the absolute value. So this is why it was important to identify the range of theta. So this is equal to 25 times the integral of cosine theta times another cosine theta d theta, which is equal to 25 times the integral of cosine squared of theta d theta. And so now we need to use the power reducing identity. The power reducing identity is as follows. We can rewrite this as 25 times the integral of 1 plus cosine of 2 theta, all divided by 2 d theta. Okay, so finishing over here, I'm going to pull out 1/2. So this is going to equal to, so we have 25 divided by 2 times the integral of 1 plus cosine of 2 theta d theta. Okay, now we are ready to evaluate the integral. So we have 25 over 2 times the antiderivative of 1 with respect to theta is just theta. And then we have plus the antiderivative of cosine of 2 theta will be sine of 2 theta divided by 2. And since we don't have upper and lower limits, we need to include plus c. We're almost done here. We still have to replace all the values of theta and replace them in terms of x. So I can't evaluate sine of 2 theta using this triangle because it's in reference to theta, not 2 theta. So I need to somehow rewrite sine of 2 theta so that I can only obtain values of theta inside of a trig function. So we can use what we call the double angle identity. The double angle identity says that sine of 2 theta is equal to 2 times sine of theta cosine of theta. So I'm going to write that. So here this is equal to 25 over 2 times theta plus 2 sine of theta cosine of theta all over 2, and don't forget plus c. And now the 2's will cancel, so we have 25 over 2 times theta plus sine of theta times cosine of theta plus c. Okay. Okay. And now we can go ahead and substitute back the value of theta, sine theta, and cosine of theta. So this is equal to 25 over 2 times theta. The value of theta is sine inverse of x over 5. So we have sine inverse of x over 5 plus the value of sine of theta, which we know here, sine of theta is x over 5. So here we have x over 5 times the value of cosine of theta. Well, cosine of theta is equal to the adjacent side over the hypotenuse. The adjacent side of the angle over the hypotenuse, right? So here I can say times the square root of 25 minus x squared over 5. And don't forget to include plus c. So how about that shortcut that I promised you from the beginning? Well, if you recall, when I started with the square root of a squared minus x squared, and I substituted the value of x and slowly manipulated it, I was able to come up with the equation the square root of a squared minus x squared is equal to a cosine theta. So I can take the integrand, because it's already in the form a squared minus x squared all under the square root. I can literally replace this with 5 cosine theta because we said that they were equal. So if I started here, I would have the integral of the square root of 25 minus x squared dx would just simply equal to the integral of 5 cosine of theta, and of course you still would want to replace dx with 5 cosine theta d theta, so that's still multiplied by 5 cosine of theta d theta, and then 5 times 5 is 25, so that's 25 times the integral of cosine squared of theta d theta. And look, we have 2 steps. We're already here. Look at all the steps that we could skip, okay? So this line is equivalent to the line here, okay? But you gotta be careful because it's not always going to be set up like the square root of a squared minus x squared. For example, it could just have a squared minus x squared. So if you just saw a squared minus x squared, then you have to be careful, because then in order to make that equivalent, you would need to manipulate this equation. I would need to take the square. I would need to square both sides so that a squared minus x squared would equal to a cosine theta squared. So you just have to be careful. But for sure, it will always work out nice when you go about it in the fashion that I have shown you in this example. And that is how you evaluate integrals using trigonometric substitution. Thank you for watching, and I will see you in the next video.